Welcome to week 3 of Weather and Climate. Our topic tonight is air temperature and moisture in the atmosphere. If you remember last time, we talked about radiation, which travels 93 million miles from the sun and reaches the Earth, eventually the Earth's surface. The sun produces all forms of radiation, but because of the sun's temperature, the maximum output of radiation is in the visible part of the spectrum. About 50% of that radiation penetrates through the atmosphere and clouds and makes it to the Earth's surface and is absorbed. The Earth then re-radiates that energy, but in the new form of infrared light. And so this is where we begin the heating of our atmosphere from the ground up. So it's this infrared radiation which begins first at the ground as the Earth releases the heat that it had absorbed from the sun's energy. So that each day is like a tiny season with a cycle of heating and cooling. The sun, only out for a certain period of time, provides that energy, but there's a lag time, so the heating always happens later than when the sun provides that initial energy. That's because it takes time for the Earth to heat up. Air is generally considered as a poor conductor of heat, so initially the heating only affects air next to the ground. So it is a slow process. The sun can be out for a few hours before the atmosphere begins to warm up, and typically the peak temperature of the day occurs later in the afternoon, well after the sun's rays are the most direct and most intense. Now, the warming of the air near the ground begins convection, so the air becomes less dense and it begins to rise through the surrounding air that is more dense, and cooler air begins to fill its place and begins to heat closer to the ground, but that helps to distribute warm air to the higher parts of the atmosphere, helping to deliver heat. This picture really helps to depict the contrast of temperatures just within a body's length away from the ground. As you can see here, the closer you are to the ground, the warmer it is in the daytime. So when you're very close to the ground, temperatures could, in this example, on a hot day, could be somewhere close to 120 degrees if you're right near the road, the concrete. But at about 1.5 meters or 5.5 feet, where this thermometer is taking the air temperature, it's closer to being about 90 degrees rather than 120. And so it's important that when air temperatures are taken, that there's some consistency about where the air temperature is being taken. And since a lot of people fall around this range in height, the air temperature is typically taken that far off the ground.
As the sun rises in the morning, the Earth's surface warms more quickly than does the air above. On a clear, calm day, the air in contact with the surface normally reaches its highest temperature at noon, when the sun's energy is most intense. However, the air several meters above the ground, where thermometers are usually located, typically reaches its highest temperature later in the afternoon. At night, the ground cools more quickly than the air. This situation causes the air in contact with the ground to become colder than the air several meters above, and the temperature inversion forms just above the Earth's surface.
that video really helps to illustrate the cycle that goes on throughout the day. Some details that we'll address very shortly. If we look at the daily temperature and solar energy chart, we can see that there are some slightly different contrasts. What this graph shows in this region is the lowest temperature of the day. And then as the day goes on, the temperature rises, and then we reach a maximum where it's the highest temperature of the day, and then the temperature begins to fall. So when do those maximum temperatures happen? Well, you can see that on this particular day, sunrise is at 6 a.m., sunset is at 6 p.m. 12 hours of day, so therefore 12 hours of darkness. Now, we say that the coldest time of the day is right before sunrise, because as soon as the sun's radiation begins to heat the earth, the air temperature will gradually begin to increase. So we do get an increase in temperature, and so we've bottomed out right as the sun begins to rise. The peak solar radiation, where it's most intense, is right around noon. And so you can see that we are from 6 a.m. to noon increasing the amount of energy that we're receiving from the sun. After noon, the sun begins to get lower in the sky. The rays become less intense as the angle increases that they strike the Earth's surface, and so the rate at which we're receiving energy begins to decrease. But the Earth's surface temperature, the air temperature near the surface, continues to increase because we still have more sunlight coming in than we have Earth cooling going out. But at some point in the mid to late afternoon, as the solar energy continues to decrease, the amount of outgoing energy equals the amount of incoming solar energy, and it's at that point the Earth is no longer able to warm up any further. Past that point, the Earth is losing more heat than it is gaining, and so the temperature at that point then begins to fall. The sun is still out for another hour or so, and it still feels pretty warm. So the decrease in temperature is gradual, but it begins to decrease. So the sun doesn't have to set for that decrease to begin. The important thing is when these two graphs cross, that is the point in which the incoming energy is equal to the outgoing energy. But as soon as that maximum is reached, the Earth begins losing more heat than it does gain solar energy, and therefore it begins to cool down. Just a few factors that determine how warm the air becomes will include the type of soil, the moisture in the air, and the amount of vegetation cover. All of this will ultimately impact how much the Earth is able to absorb in terms of heat, and therefore how much energy it's retained in order to give off. We mentioned that the sun sets, causing the rays of the sun to spread out, giving off the same amount of energy over a wider surface area, and so everybody's getting less energy overall, and so therefore that reduces the amount of heat that's available to warm the ground. So ultimately, radiational cooling begins as the Earth begins re-radiating infrared light, infrared energy, away from the ground into the air. Eventually, a radiation inversion, like you saw in the video, will form as the air above the ground cools more slowly than the air closest to the ground. The air closest to the ground will cool much quicker at night, and so you'll see a switch in the curve on the graph. So I'll show you those two graphs here. There we see the daytime graph. Notice the curve. Closer you are to the ground, the warmer it is. The higher up you go away from the ground, the cooler it gets. At nighttime, the curve flips. So now, the closer you are to the ground, the cooler it is, and the higher up you go, the warmer it is. So that's the temperature inversion. The curve flips as the day goes on when you go from day to night. And that's because the Earth's surface loses heat faster than the air. Just as much as the air is a poor conductor and to retain heat, whatever heat it does manage to get, it has a harder time letting go. This type of temperature inversion happens on cool, clear nights along these types of valleys. So cold, dense air sinks along the hillside and sort of provides colder than normal temperatures at the bottom of the valley, and the area just above that remains above freezing is referred to as the thermal belt. So this is the area that was initially heated through the day, and that heat through convection warmed this area here. So the cooler temperatures towards the surface show up as low as possible. But remember, as you continue to rise, the temperature has to begin to drop at the adiabatic rate as we climb higher into the troposphere. So this small temperature inversion happens closer to the ground, where this is essentially the graph that we saw here. Okay, close to the surface, but then at a point above the thermal belt, the temperatures begin to cool again. So this is where you see it going back down. One of the toughest issues with dramatic drops in temperatures at night is in agriculture, trying to protect crops from getting ruined in the extreme temperature differences and the low temperatures. So they've devised different ways to try to protect crops from freezing overnight. This heater warms water so that it can help get convection going, so some of that cool air that's near the surface gets heated and then will rise and help to circulate the air a little bit more, take some of that cold air away from the surface. You can also use these air generators, essentially very similar to windmills, which will mix the air. Remember, the air above the ground at night is typically warmer than the air closer to the ground. So by mixing, we can get some of that warmer air to sink and some of the cooler air to rise above the ground and away from the crops. And believe it or not, another method is to actually coat your crops with water and freeze, because that freezing will stop any sort of issues with the crops going bad for a short period of time, keeps them free from the rest of the elements, acts almost like a protective case. Every day, temperatures vary slightly. You don't get the trend that we saw early on where the temperature follows a specific curve, because that's an ideal situation, and every day presents its own set of factors which will affect exactly how the temperature changes throughout the day. Some factors which affect the daily or diurnal range of temperature is definitely cloud cover and moisture in the atmosphere. Think that clouds help provide a blanket in the atmosphere. So during the day, clouds will help reflect light back out into space rather than let it reach the earth. And so a cloudy day won't be as warm as a clear day, because it prevents that initial solar energy from actually reaching the Earth's surface. But on the other hand, a cloudy night keeps heat trapped closer to the surface and allows the nights to be more moderate rather than more extreme and a rapid cooling. So you'll notice that when it's cloudy overnight, the temperatures don't fall quite as much as on a clear night. And every location has its own slight variation, but what's usually provided on television through weather forecasts is a mean or average daily temperature. Temperature variations along the surface are always much more extreme between day and night than some height above the Earth's surface. So take it at ground level here. In Celsius, you have that the high for this day is 21 degrees and the low is 13. So that's an 8-degree difference in Celsius scale. But notice if you go all the way to the top of this building at 300 meters above the ground, the high was only 17 and the low was only 13. So that's only a 4-degree difference. So the temperature contrasts from day to night are not as extreme the further away you get from the surface, and more extreme the closer you are to the surface. Here you can see what cloud cover does. So on a clear day, plenty of sunlight is able to warm the Earth's surface, allowing for infrared light to warm the air closest to the surface. Whereas at night, with no cloud cover, all that infrared radiation is given off and escapes into the higher parts of the atmosphere, and so the Earth cools much more rapidly. On a cloudy day, not as much sunlight penetrates through the clouds, more sunlight is reflected back up into space, and so even though this could be on the same day in the year, cloud cover would produce a cooler day, and then at night those clouds help to retain heat, and so you'd have a warmer night. So clear skies produce a much more extreme variation in the daily diurnal temperature, whereas clouds help to moderate temperature variations. Now, on large scales, there are some what we call regional temperature variations. These temperature controls are those factors that cause variations in temperature from one place to another, typically in larger scales. Some of those factors include latitude, how far north and south you are from the equator. The closer you are to the equator, the more you are receiving those direct rays from the sun. Land and water distribution refers to where your position is within a continent. Are you closer to an ocean or a body of water, or are you very far removed from a body of water and mainly continental all around you? Ocean currents. The oceans are responsible for delivering warm or cold water to those coastlines. So you may be near a shore. You could be along the Atlantic coast or the Pacific coast, but depending on the direction of the ocean current, you might be exposed to to cooler water temperatures or to warmer water temperatures, which ultimately will affect air temperatures. Elevation is another factor. So the closer you are to the ground, the warmer you should be. The higher the elevation, the cooler it will be. This is a map which shows isotherms. These are lines of equal temperature. So if you follow any one of these lines across the map, you're staying constant in temperature. And if you cross from one line to another, you're going in between temperatures. So for example, this line right here is the 70-degree isotherm. And as I go along this line, I'm staying at a constant 70 degrees in temperature all the way across the globe. If I go from this line to this line, I go from 70 through 69, 68, and so on, all the way down to 60 degrees. So by crossing over isotherms, you're changing in temperature. Notice that none of the isotherms ever cross. They always have to stay parallel to each other. You'll see that this is January, so the warmer temperatures are going to be in the southern hemisphere, close to the tropics. The Tropic of Capricorn is around here, so you're going to see the warmer temperatures. Some of these peaks where you have to go further towards the north to get some warmer air is due to the ocean currents. Here you can see part of Australia is peaking in the highest temperatures in this region, and that's because it is away from any body of water. Because it's January in the northern hemisphere, it's winter. So you're going to see some very low extreme temperatures close to the North Pole here. And even colder temperatures inland, away from any of the bodies of water. But if you're close to the coastlines, it's a little bit more moderated. You'll see that part of this pattern will flip when we get 6 months later in July. Now it's the northern hemisphere, right along the tropics here, that experience the warmest weather. This area, which is the Sahara Desert, has the most intense heat in July, the most intense rays from the sun, and is deprived from a large abundance of water, being that this portion is in away from the coast. So you're going to get these areas where it gets very hot. The cooler temperatures are closer now to Antarctica because it's their winter in July. Notice the variation of these two places, which are located at the same latitude. So whereas we said in the last slide that latitude makes a difference, but here we have two locations that are at the same latitude, and the difference is now that you have this city in the middle of a continent and you have this city in the middle of an ocean. Continent temperature variation is going to be more extreme because of the way the Earth retains heat. So the Earth absorbs more heat in the summer and not as much heat in the winter, and so the variations are much larger. In the ocean, the variation is less. It's harder for this city to get as much radiation as this city, but it doesn't lose as much heat over the winter months because, one, of ocean currents, and two, water retains heat a lot more efficiently. It takes a long time to heat water compared to land, but it also has a harder time releasing heat. So this is typically why the couple things, that the ocean temperatures always seem to be cold when you go down the shore at the beginning of the summer. It's usually around this time or around the end of the summer that you see the warmest ocean temperatures. It just takes a long time for the water to heat up. But also you find that the shore is typically cooler during the daytime than in the city. A lot of people go to the shore to find some relief, and that's because of the cooler ocean temperatures and what that does to the air. And so you can moderate the air temperature around big bodies of water. And here we have San Francisco and Richmond, Virginia, which are located at the same latitude as well, 38 degrees north. And we have a very interesting looking contrast in the temperature variation curves. This is specifically due to the fact that they're on two different coastlines. Along the Atlantic, water flows up from south to north in the Gulf Stream, which delivers warm water, and so we're able to get these higher peaks, but the water is cooler in the winter, and so you have the lower troughs. Over in San Francisco, it's different. The water flows from north to south along this coastline, and so generally the temperatures stay cooler on average in the winter and don't really fluctuate too much. As winter comes around, some warmer water gets circulated through up in Alaska. Not terribly warm, but warm enough to not cause such dramatic dips in the temperature. So a lot of times when we measure temperature, we're concerned about how we're going to feel in that environment. So sensible temperature is our perception of how the air feels in terms of temperature. The body heats up primarily through metabolism. So our bodies maintain internal heat at a little over 98 degrees, but there are certain things that we expose ourselves to externally that can cause skin damage and ultimately organ failure if it persists. So one thing is low temperatures promoted by the wind. So it's always colder when it's windy outside, because that helps to remove heat from your body a lot faster. Since we are maintaining a constant body temperature of 98 degrees, just like the Earth, we are re-radiating out from our bodies infrared light. And so the wind helps to stir the air a little bit more, and robs your body of heat. And so we have what we call a wind chill index that tells us how much colder wind will make it feel. So it's not the temperature, but because we're being now robbed of our heat at a faster rate, because air is carrying it away faster through the wind, we will say that it feels colder. And long exposure to that can cause frostbite and hypothermia. Now, in contrast, when we're out in warm weather, your body has a way of cooling down by enlarging blood vessels and then evaporating sweat off your body once you perspire, and that leaves your external body feeling cooler through that process of evaporation. Here we have a wind chill factor table. What you're going to see here above is the temperatures. So we have 40 degrees is really where we'll begin talking about wind chill as being a factor. And then the temperature goes all the way down to negative 40 degrees. If you go down this list, this column is reserved for wind speed in miles per hour. So a calm wind is like next to nothing. 5-mile-an-hour wind, 10-mile-an-hour wind, and so on. So the way you read this graph is, if the wind was otherwise calm, the temperature would be 40 degrees. But here, if the wind picks up and it's now 5 miles an hour, it feels like it's 36 degrees. The air temperature is still 40, but it feels like 36 degrees. When it's 40 degrees outside and you have a 30-mile-an-hour wind, all of a sudden now you've dropped below freezing and it feels like 28 degrees. So any of the areas that are shaded darker are areas where frostbite can occur in less than 30 minutes. So this area over here. So if the wind is close to being calm, the air temperature has to be very cold for any type of frostbite to settle in. But then again, the air temperature doesn't have to be terribly cold if there's high winds involved. An instrument that many people are familiar with in terms of measuring temperature is the thermometer. There are different kinds. Essentially, you have the liquid in glass thermometers, as well as some other electronical types of thermometers. The size and scale of a liquid thermometer depends on the type of liquid that is in it and its properties. So you have this bulb which contains most of the liquid, and it heats at a certain rate. It causes that liquid to expand upon heating, which then allows for it to rise through the tube. And so specific temperature changes are recorded as a different expansion of the liquid inside of that glass tube. And so you would try to read where the liquid at the bottom of the meniscus, which is this little dip inside of the top of the liquid. You would measure it at the base of the meniscus. These digital devices are also picking up in a similar way the temperature of the air. And rather than use liquid, here we have a piece of metal. And there are small fluctuations in this metal when it's heated. So it will move in a way, contort, stretch, contract, depending on the temperature. But the motions are typically very small for the types of temperatures that we're concerned with. And so there's a lever which helps to amplify the motion. So a little motion here causes a big motion here. And so it's calibrated so that way it can record it on this piece of paper. As the paper spins, it records the temperature changes over time. The last topic we're going to cover, we're going to go a little bit into Chapter 4, the rest of which we're going to cover next time before you're required to take Exam 1. And we're going to just focus on moisture in the atmosphere. So terms like humidity and dew point are some things that we'll have to review. We all know that water and water vapor is very important in the way the atmosphere works. We know that water vapor in the atmosphere will cool and turn into cloud droplets and ice crystals, which can eventually grow in size and fall back to the earth as precipitation. When we use the term humidity, this is a quantity which describes the amount of water vapor in the air at any given time, which is certainly not a constant by any means. This fluctuates every day throughout the year. It's important to know how water gets around through the atmosphere, through these three basic parts of the water cycle. Evaporation happens when the sun's energy transforms huge amounts of liquid water into water vapor and moves that water high into the atmosphere. Because the atmosphere is cooler, the water condenses back into a liquid form, which we see as clouds. Now, typically the clouds are light and are held up by air currents, but once water droplets have become large enough, gravity takes over and overcomes the uplift by the air, and the water returns back to the ground in some sort of form of precipitation, which could consist of rain, snow, or hail, as well as some other variations. And all the water on the earth has essentially been recycled throughout time. Most of the water was delivered to the earth very early on in its history by impacts from large space objects, but otherwise we get small deposits of water in the form of ice through smaller impacts over the course of recent time as well. But generally, the majority of the water that's on the earth now has been here for a while, and so that includes your drinking water. It's been recycled through this water cycle for as long as the earth has been around. Now, the space around us seems pretty vacant, and but we know it's filled with air. But even then, we still can't picture the idea that there's a limit to how much vapor we can actually store in the atmosphere. But eventually, it is possible to add too much water vapor to the air, where there's not enough room between all the molecules of gas to keep them sort of tucked away in the atmosphere. So saturation occurs when the total number of molecules trying to escape a liquid balance with the number of molecules that try to return back to liquid. So here we have an open jar on the left, and there you can see with the conditions of the air you have at times water that is evaporating and leaving the jar, and at times water that is condensing back into the jar. Now, if the rate at which evaporation occurs is greater than the rate of condensation, then you'll see over time that the jar will decrease in the amount of water that it has. But for as long as the water has a chance to escape, the air is considered unsaturated. But you put a lid on it, and eventually there's the amount of water that evaporates will equal the amount of water that tries to condense back into liquid form, and you get a saturated environment where you cannot fit any more water vapor molecules into the air above the liquid water. And so you can see here that here we have the water vapor molecules in warm air are sort of moving very quickly. In cool air, they condense and get very close to one another. This picture essentially shows how clouds can begin to form. Water will try to condense onto small surfaces, which we call condensation nuclei, and that helps them to form into larger droplets. But if it's warmer, they bounce right off these nuclei and keep moving. There's a variety of ways to describe the amount of water vapor in the air, and sometimes it can get confusing. Absolute humidity is by definition a density, which is the mass of water vapor contained inside a volume of air. So this just tells you how much water there is in the air right now. Specific humidity compares masses. So we're comparing the mass of water vapor with the mass of air with the water. Okay, so how much of the total mass of the air with the water inside is water itself. So you're comparing just the water with the total air around it. The mixing ratio is a comparison of the mass of water vapor with the mass of dry air. So all three of these ways try to describe for us how much water content is in the air right now. One typical way that meteorologists go about calculating the relative humidity is by using something called the vapor pressure. So we know that the air exerts a pressure onto the surface due to the fact that there is the air has weight because of gravity, and that pressure is roughly 1,000 millibars at the surface. And so the pressure is felt throughout along the surface, and but in a parcel of air, 78% is due to nitrogen, and so the partial pressure of the air due to nitrogen is about 780 millibars. Oxygen makes up 21%, So that's about 210 millibars. And then water occupies something very small, about 10 millibars of partial vapor pressure, and that number can change depending on whether or not the air is hot, is warm, or cool. When the air is warm, the space between the molecules expands, and so you have more room in the parcel to squeeze more water. So you can fit more water vapor, and the partial pressure of water vapor increases. So in a cooler parcel, you wouldn't be able to fit as much water, and so generally the vapor pressure is lower. The saturation vapor pressure is how much, and then we're talking specifically about water right now, but how much water vapor you would have to squeeze into a parcel of air so that that air reaches saturation at that given temperature. So the saturation vapor pressure is going to be a lot higher in warmer conditions because you can fit more water. So it's going to take more water to reach saturation. You could squeeze more water into air without it reaching saturation, and so that'll increase the pressure. So if the air is warm, the saturation vapor pressure is going to be high, and therefore you're going to have more water in the air. The saturation vapor pressure at lower temperatures is going to be lower. So you can reach saturation at a much with less water in the air when the air is cooler. So typically in the morning you're going to see dew and fog, and that's mainly because the air is cooled so much. During the day it's warmer, therefore you're able to have a lot more water vapor in the atmosphere, typically through evaporation throughout the day. But then so that water vapor stays in the atmosphere overnight, the air cools, and so the atmosphere's ability to hold moisture, to hold water, becomes diminished, and so the saturation vapor pressure of water decreases. And so you still have all that water in the air, and so without adding any water, overnight you could reach the saturation vapor pressure, and that results in the air becoming saturated. And so you see that as the dew begins to form, or fog might condense along the surface. So here's a parcel of air. The parcel's not really bound by any structure. It's just, you imagine a bubble surrounding a part of the air, and in there you can see the nitrogen molecule, the oxygen molecules that are all paired up, and then water vapor. So that is the water molecules have one oxygen atom in red and two hydrogen atoms in white there, and they're always moving around. If that parcel is warm, it will become larger. The bubble will be larger, containing still the same amount of molecules. So in that parcel, you can now squeeze in more water molecules and still have enough room to not reach saturation. As long as there's still space for them to move, then you have not yet reached saturation. But if you cool this bubble down, this bubble becomes smaller, and so the water that's already in here, which may not have saturated the air, once this bubble gets smaller, everything gets closer, and all of a sudden now the bubble becomes crowded, and the water molecules don't have enough room, and so the bubble reaches saturation. The calculation for relative humidity is pretty straightforward. You take the actual vapor pressure of the air, which is a description of how much water is in the atmosphere right now, and you divide that by the saturation vapor pressure. That means how much water you will need to put in the air to reach the 100% humidity, which is where the atmosphere can't hold any more water. And that'll give you a ratio, and so you multiply it by 100%, and then you have a percentage. And that's usually how we represent relative humidity. So the two ways you could change relative humidity, as I touched on a little bit already, is changing how much water is in the atmosphere and changing the temperature. You can increase the relative humidity by adding water. So if you keep the temperature constant, you can have maybe a 75-degree day with no water or very little water in the atmosphere, and it would feel very pleasant. And then if you were to increase the water content, all of a sudden it becomes a little bit more muggy, and it feels a little more unpleasant in that kind of environment. So the closer you get to 100% humidity, the more unpleasant the air becomes. And that's mainly due to the fact that as your body overheats, it tries to cool down by sweating, and the sweating itself doesn't really cool your body down. It's the evaporation of the sweat off your body that ultimately leaves you cooler than you were before. Now, if the air is saturated, there's really no space for water to evaporate from your skin, and so you just become really wet and sweaty and not really as cool as you would be if you were in a low humidity climate. Temperature can also affect the humidity, as we mentioned before, that if you keep the amount of water constant in the atmosphere, heating the air will decrease the relative humidity, but cooling the air would increase the relative humidity. So think, as you add more water vapor, you increase relative humidity. As you increase the temperature, you decrease the relative humidity at constant vapor pressure. So that is essentially what we call an inverse relationship that temperature has with relative humidity. As one goes up, the other one goes down. If the temperature decreases, that causes the relative humidity to increase. This curve helps to illustrate the saturation vapor pressure for water. So how you would use this graph is first determine the temperature outside. So on any given day, it could be any one of these temperatures, and so you would find the temperature and you would follow it all the way up to this red curve. And once you find the red curve, you're going to go over to the vertical axis and you're going to read the value on this axis, which represents the saturation vapor pressure. So on a 50-degree Fahrenheit day, the saturation vapor pressure is somewhere around 12 millibars. So if the saturation vapor pressure of water reaches 12 millibars on a 50-degree day, you know you've reached 100% humidity. Because I would do 12 divided by 12 times 100, that would be 100. You can see here that if the temperature is higher, you got to go up higher on this curve, which means that the saturation vapor pressure is going to be much larger. That means that the atmosphere can store more water in the space between the molecules. Relative humidity and dew point go with one another. Dew point is a temperature. It's the temperature at which saturation will occur. So we know that temperature has an inverse relationship with relative humidity. So given that the amount of water in the atmosphere doesn't change over a period of time, the dew point would represent the temperature you'd have to decrease the atmosphere by, or decrease it to, in order to reach saturation. Okay, so an example might be, let's say the saturation vapor pressure was 12 millibars, but the temperature was 86 degrees. The relative humidity would be pretty low. You do 12 divided by, this value here is about 42, and multiply that by 100, and you get roughly 29%. That's a low humidity, and therefore that 86 degree weather out there, even though it's pretty hot, will feel fairly comfortable. The dew point under those conditions, rather than tell you the humidity is 29%, I could tell you that the dew point is about 50 degrees. So what does that tell me? That tells me that if I want to saturate this air, we're currently at 86 degrees, but the partial pressure is 12 millibars. So that's fairly low. You'd have to make it 42 millibars to cause saturation at this temperature. I would have to cool the air from 86 degrees all the way down to 50 in order to saturate the air. So because there's such a huge gap, the greater the difference between the dew point and the actual air temperature, the more comfortable it's going to feel. So the greater the air temperature and the dew point are from one another, you can determine how humid the air actually is. If the humidity is low, that tends to mean that the air temperature and the dew point have a large difference. Whereas if it's really humid, then the temperature is fairly close to the dew point. So you can see some of these temperatures here. So comfortable dew points are typically in the 50s. What starts to be a little bit uncomfortable is in the 60s. And notice we're now going between the upper 30s and the lower 50% relative humidity. But by the time you get to the 70s, you're already in an uncomfortable position to be in. And then above the 80s, it becomes pretty hard to manage, and can cause some health issues for people, especially if it's also really hot outside, which these numbers go with respect to a 90-degree air temperature. If you look at these curves, it seems that they might be backwards, but for good reason. The red curve represents the temperature changes, which we've discussed before. The lowest temperatures are right before sunrise, so on average right before about 6 a.m. for many places, and then the temperature peaks right before sunset, So that'll be around before 6 p.m. Remember what's happening here. If we keep a constant vapor pressure or a constant amount of water in the atmosphere, the daily temperature variation is going to cause the humidity to naturally change. When the temperatures are cooler, the air doesn't have the ability to hold as much moisture, and so therefore the humidity is going to be at its peak, its maximum. As the air heats up, the humidity comes down because now the atmosphere has more room to hold moisture. When the temperature peaks and it's at its highest, the relative humidity should be at its lowest. This is assuming we don't change the amount of water in the air. So it should get more pleasant as the day goes on, but a lot of times in the summer especially, we also get a lot more evaporation, and that adds water into the atmosphere, and so it changes this picture a bit. So what this is representing are average dew points for the month of January. So you expect the dew points to be low, and that's because it's not because it's so pleasant, but more because the temperatures are lower. So to reach saturation along this line, you'd have to drop the temperature to 0 degrees. But look at Florida, in particular Miami Beach, where it's warmer. The temperature has to be 60 degrees to reach saturation with 100% humidity, which may very well be possible down there, and so it's going to be pretty humid climate anywhere along the coast here, but in the middle of the country, the dew points stay fairly low. That drastically changes in the summer, so this is in July, and remember we said anything above 70 becomes a little bit hard to handle, and so this area here is always fairly humid. This area in this darker green still on the limits of what people can consider comfortable, but if you go out west near the Four Corner states, you're going to be in an area that, even though the temperatures may be very high, is much more bearable because of such low humidity. So you tend to see that with desert-like climates. In this picture, you see this cloud which has developed, which shows that the temperature, which is fairly cool, is equal to the dew point temperature, which is this TD. So why is the dew point temperature low compared to this dew point temperature? That's because at this level in the atmosphere, the atmosphere itself is cooler, so it has less capability to hold in moisture. So once the temperature reaches the dew point, it is now at 100% humidity and begins to condense out, and so that's where you have clouds forming. Below the cloud base, the air temperature and the dew point are different. Dew point is lower, but not by much. The difference is small, and so the humidity is high, and so we get this rain in this area. As I mentioned before, it's usually the humidity that people complain about rather than the heat itself, and that's due to the fact that your body is unable to cool itself off by the means of evaporation off of your skin, because there's just no room for the water in a highly saturated atmosphere. A term that we're going to need to know is wet bulb temperature. This is the lowest temperature that can be reached by evaporating water into the air. So again, that is a cooling process. So if you wet an object and then have it evaporate off that object, it will leave the object cooler than it was. But how low the temperature gets will depend on how much water can evaporate, and how much water can evaporate will depend on the humidity. The heat index is sort of analogous to the wind chill factor in the winter, heat index in the summer. This combines air temperature with relative humidity to determine what it really feels like to people. So again, similar to the wind chill chart, you have two pieces of information: the relative humidity and the air temperature. So if the humidity is low, no problem. The air temperature is roughly the same, or even it might even feel better at really low humidities. But let's say if you're close to 100% humidity on a degree day that's 82, it might feel as hot as 96 degrees. So that's a 14-degree increase that it feels like. And so at that point you would want to have extreme caution, because your muscles can start to cramp and begin heat exhaustion if you do work outside. So even on an 82-degree day, which temperature-wise isn't too bad, if you're 100% humidity or close to it, you're at a point where you have to pay attention and take extreme caution. But once the temperatures get higher, then it really doesn't take much humidity to make it feel unbearable. So if on a 100-degree day the humidity is about 40 degrees, that's or 40%, that's not a high humidity, but on a 100-degree day, that's a dangerous situation to be in. And on that same 100-degree day, we were in the 70% range. We would have an extremely dangerous situation where the risk of heat stroke or sunstroke is very likely. And that's because, for it to be so hot and for the humidity to be so high, there must be a lot of water in the atmosphere, and that makes it very hard on your body to breathe and function correctly. In terms of measuring humidity, the tool that we commonly use is something called a psychrometer. You basically have two thermometers that are attached on a sling that you're able to spin around. The one thermometer is just a normal thermometer, and on the other thermometer at the bulb end, you typically place a cloth which is then wet. It's soaked in water, and when you spin both thermometers, the normal thermometer gets the air temperature, but the one that has the wet cloth around the bulb gets you what we call the wet bulb temperature. The hygrometer is another way to measure the amount of moisture in the air. So I'll show you an example of the hair hygrometer in particular right here. So here we have, in this case, human hair. which, similar to the bimetallic strip that we were looking at to measure temperature differences, here human hair expands and contracts by absorbing and releasing water. So depending on how humid it is, the hair will either expand or contract by a little bit, but by enough that if amplified by this lever will cause a shift in this needle to help indicate the changes in the amount of moisture in the air. The sling psychrometer looks like this. Here you have the dry bulb that gets the air temperature, and the wet bulb, which is soaked. And so this wet bulb temperature should be lower because as you spin the psychrometer, because there's a little handle here and you'll spin the psychrometer around, as you spin, the water will evaporate into the air. The more water that's able to fit into the air, the lower the wet bulb temperature is going to be, and the greater the difference between the dry bulb and the wet bulb temperatures, the lower the humidity. So here's this chart where you can look up the current dry bulb temperature, in this case in Celsius. So you would swing the psychrometer around, you would look down at the dry bulb and say, okay, the temperature is 22 degrees Celsius. And then you would look at the wet bulb temperature and you say, okay, the wet bulb temperature is reading 16 degrees. So you say, what I need to find is the difference between the dry bulb and the wet bulb difference. So 22 degrees is the dry bulb, 16 degrees is the wet bulb. The difference is 6. So that's what this 6 represents, is the difference between the wet bulb and the dry bulb temperatures. Okay? So you don't see the 16 that I mentioned here, but that's where the 6 comes from. In order for you to have chosen this 6, you would have had to read the wet bulb temperature as 22 minus 6, which is 16. But so again, you would read it as 16, so you do 22 minus 16 to get 6, and then where these two, the row and the column, meet is 12 degrees, and that is your dew point. So that's for calculating dew point. There is a similar chart that would help in calculating the relative humidity, which involves the same process but a different scale. If you have any questions about any of this material, feel free to discuss it in this week's posts, and also shoot me an email, and I'll be sure to get back to you as soon as I can. Have a great week.